Okay, thank you to be here for the lecture of today. Let me consider again, let me repeat this exercise which I proposed last time. Now, we have again, we can see here the data which I have, which I will give you also in the exam, in order to be clear what is given and what is not. We have basically a coil, a rectangular coil. Rectangular means we can see here. Something probably. Yeah, that's it. A rectangular coil means the coil which can be seen here. Very often we are thinking that the coils are circular. It's not valid. This idea or this hypothesis. We have many motors, many devices, actuators, rectangular or quadratic coils. Anyway, we have a coil with 10 windings. 1, 2, 3, and so on. The dimension is, we have 2 dimensions, rectangular, A and B. And look, here we are in the presence of 2 permanent magnets. The representation a little bit with fantasy. Try to think that we have 2 couple of magnets, or the 2 magnets, better to say. Node, we have inverted magnet, permanent magnet. Do you remember I told you that the inversion of the permanent magnet is also in the practical application usual? Do you remember some possible some devices, real devices which I showed you last time, no? With this motor applications on actuator for motor application. Anyway, here we have a permanent magnet oriented north in the room, in the, let me say, in front of the blackboard, and south behind. This means the line, we can image the flux from this position to in the direction of blackboard. This means we indicate with plus, is going through the blackboard or out, if you want. And the other one is inverted. This means the north pole is behind the blackboard, as if the flux is coming on this part. They inverted. I don't know if it's clear what I intend. North is in this position, and the first part, south in the other part of the room, and in this case here. And in the other part is inverted. The north is behind the blackboard, and the south is here. Therefore, we can see plus in this region here, minus this region here. This means the flux is inverted, or the flux density. Do you remember? B is the flux density, which is the flux divided the surface. Okay, this I clarified the dimension. A given, yeah, very important that we are moving, this is the hypothesis, with a constant velocity, 2 meters per second, in this direction, basically go inside. The coil go inside. How the coil go inside is not given. I didn't tell you. But of course, we can imagine that if the velocity is constant, in accordance with what I told you last time, we have a force. If you remember what I told you last time, we'd push the coil in this direction. We compensate exactly this Lorentz force, which works against, because of the eddy current. If you want, you can consider also eddy force if you want. acceleration is zero. No? If the velocity is constant, acceleration is zero. This means we don't consider the mass. So acceleration is zero, the mass doesn't play any role. In the dynamics, we don't have dynamics, I mean the movement. It's just a kinematic concept because the acceleration is zero. Easy example. If the acceleration is not zero, it's a differential equation. Here in this course, we will consider just a little bit the idea to understand what happens if the acceleration is not zero. We will see today also what happens is L is not zero, inductance. Here is really something extremely artificial, just to verify, just to have a little bit confidence with the concept of Lenz, Lorentz, and so on. Because if I have a coil, if I have a windings, we have inductance L. Here it seems to be that inductance L is zero. Nevertheless, we can consider inductance L is not zero, but we have the constant current. But anyway, the problem is connected. It's really an artificial case. But today we will see in a real case. We will consider also in a real case in which acceleration is not zero. Then we have to consider the mass of the mover of the actuator. We have to consider L not zero. But let me do this exercise. The question in the exam is, please graph flux in this phenomenon. This means during the movement over time. I don't remember, induced voltage, induced current, what the power, mean value of the power, what force, brake force, mechanical power, so something like that. I don't remember which kind of question, but we will see together. And during the graph, please point it out when, let me say, change happen, at which time and what is the value. Basically, the relevant elements in the graph, when something changes. In the exam, I will formulate exactly more formally, but now, scrolling down the solution, we will see what I intend with the important changes. With something that is important to point it out. We can see here a little bit already some answer. No? At which time something happens, important for the phenomenon which we want to describe. Okay. We have seen last time that the graph of the flux looks like something like that. We can see what I intend for the changes. T1, T2, T3, T4, they are extremely important for this graph because at T1 we have the maximum flux. At T2 the flux is zero. These two elements are relevant. So it's the maximum. It could be that could be interesting for some reason. So zero. So T3 is the maximum, but negative. This is the minimum set. The T4 is the time in which the flux is zero again. Now, I don't know if you remember how to justify this profile, but it's not so difficult. It's not so difficult because if you remember that the flux, I would like to be precise, the flux is still there. But what I intend with the flux is the flux involved in the movement of the coil. This is relevant for us because an actuator consists of a mover. Actuator means act, to do something. In this case, move. This means, even though I try to explain in the text of the exam, but it's intuitive. What is interesting for us is not the constant flux that is there. The flux that is there. I cannot change. The flux which is involved in the movement of this coil, we will see induced voltage, induced current, brake force, and so on. This is irrelevant. What is this? If you remember, this flux is basically as a function, if you remember, of the effective surface. I don't know if you remember this. I showed you what I intend. Because if you remember the definition of the flux density, the flux density is basically the flux divided the surface, right? Now, here, the surface involved in the movement, we say is an effective surface, sometimes active magnetic surface or active surface directly. In the phenomenon is clear as magnetic surface, change over time because moving this geometric surface inside the magnetic fields, this dimension isn't constant, B, but the dimension involved with change in the other dimension involved in the magnetic fields, which change over time, is basically this here. I don't know if is easy to see, but in any case, as we have seen in the lecture, this active surface is B multiply V velocity multiply the time. You remember in the formal lecture, as in a possible introduction, I try to clarify this concept here. No? The movement in this direction is characterized by the velocity constant. We say in physics, uniform movement. Anyway, velocity constant. This means the position change over time proportional with the time, and this proportional factor is exactly the velocity. You remember, the position is v multiplied the time, gymnasium, no? If the velocity is constant. No? If the velocity is constant, the position change over time equals v multiplied t. Do you remember this? This means the flux basically is B capitalized, flux density, which multiply V velocity, which multiply time. I don't know if you remember in the formal lecture, in the presentation, which is my study, I explained this. This means change over time linearly. In the exam, you don't need to write this B capitalized multiply V. I forgot B not capitalized, because B capitalized, which multiply B not capitalized, which multiply V, which multiply T. Because I have to consider the surface, which is B not capitalized, multiply V, multiply T. I don't know if it's clear. The surface change over time. How change over time? B not capitalized, I forgot to say before, multiply V multiply T. This is the changes, or the change over time of the magnetic surface. Multiply B capitalized is the flux. You don't need to write this because the question is graph. This means in a linear variation with respect to the time. But of course, the slope of this line is B capitalized, multiply B not capitalized, multiply V. Should I write? No, this is clear. If you look in the lecture, in the presentation is clear. Until time 1. What is the time 1? The time 1 is the time when these conductors are at this position. This is the maximal flux which we have because we have the maximal effective surface or active magnetic surface or active surface. Correct. I don't know if it's clear. What is this time when this conductor is here? is calculated here because it's A divided 2, excuse me, A divided 2, the stroke which I have to cover, divided the velocity. V is constant, otherwise it's complicated. No? In the exam, I will put V constant, not to clarify the concept. In practical application, we have programs which help us to solve complex problems. I show you what it is later. Is clear this T1 or is not clear? Should I clarify again? I have to cover this stroke. Why that? Because the maximal surface is when these conductors, we have 10 conductors, are here. Because I am moving inside, I am go out, up, I am increasing, better to say the flux. But until these conductors are here. And what is the time? Is A divided 2, I have to cover this distance here, divided the velocity, the position. If the velocity is constant, is always stroke divided the velocity. Excuse me. The time, if the velocity is constant, is stroke divided the velocity. The other relevant point which I want to know in the exam is this maximum. What is the maximum flux? This is important sometimes in the machine. We will see why it's important later in a few minutes. Is B, the flux density, multiply the maximal active surface or magnetic active surface or active as well, which is A divided 2 multiply B. B remain constant, but A divided 2 is the maximal active surface. Why that? Because when the conductor is here and the coil is going ahead, I will reduce the active surface. This I will reduce the flux because I include in the coil negative, let me say, flux. I don't know if this is clear. I'm going down. This is not clear, probably. When we have 0, when the coil is totally inside, I go up, I calculate the maximum, then going ahead, I include in the coil, in the circuit, let me say, in order to understand, negatives of flux. This means I cancel the positive flux until this position. It's complex to understand. Try to image. This is important very often. If you work with program with ANSYS, FEMLab, they calculate the computer calculate those complicated program for that. But very often we have to understand some basic knowledge, which is based on this example. Really, in order to see what we are waiting for, what we're waiting for the computer and so on. This means when did you agree? I am asking you, did you agree when these conductors are here, we are totally inside? Half of the geometric surface is positive, and half of the geometric surface is negative. Geometric surface equals magnetic surface in this position, just at this position, at time T2. Why T2 is A divided V? Because it's twice T1. It is clear this? Because I have to cover A divided 2 plus A divided 2 equals A divided V, which is constant. Then why is going negative? Because, try to imagine, the coil is totally inside, totally. This element here are here, and this element here is here. Going, let me say, right, what happens? That the positive part of the flux is excluded from the coil. And here we don't have a flux. This means if I exclude in positive, I'm going negative here. Until which position? When these elements here are here. This means half of the coil is in negative part, half is totally out. And then we have the negative maximal flux, which is exactly the maximal positive with a minus, of course. Then why? Okay, T3. T3 is easy because it's 3 times this. Because each part at the same length. Why now is going positive? Excuse me, towards 0, no? Positive in the sense, yeah, let me see, towards 0. Because when all these components or the conductors as here have the maximal negative, going right, I exclude over time more and more, linearly, of course, negative. When these conductors are here, I have the coil totally out of the magnetic fields organized in this form. T4 is 4 times T1. Huh? T4 is 4 times this, therefore 2A divided V. Now, please, in the exam, pay attention, invest energy to calculate this field, because a large part of the rest of the questions, not all questions, but in a large part, depends on this graphical interpretation of the phenomenon. Not all questions, but some of them. Look, if I ask you now the induced force, look in the data sheet, for example, and we know that the induced voltage is minus n, the derivative of t, what is the time? Minus n, and it's given. You don't need to calculate anything. You don't need to calculate anything. I mean, this, yes, of course. Calculate in the sense with a number. You don't need. Symbolically. Please proceed symbolically. As I did last time, I will give you the value in order to understand clearly what is given. But you don't need to do the calculations. You need to calculate symbolically. Understand what I say? No? You don't need to do here 0,1 divided 2 divided. You don't. But symbolically, yes, in order that I understand that you understood when something happens. But you don't need to use the calculator in this exam. This means n minus n multiply the derivative of the flux with respect to the time. Extremely easy here, because if the function of the variation is linear, n is given, minus is given. Why I have to put B not capitalized, multiply B capitalized, multiply V? It's easy because this B not capitalized, multiply B capitalized, multiply V is the derivative of what? Of this function here. Why that? Because the derivative in this case is this distance, this means phi maximum, divided this distance, because it's linear. The slope is constant. You remember in gymnasium? Of course, if I'm a complex function, you do the derivative. But here, no. Because if the slope is constant, you remember gymnasium, this divided this, y divided x. You remember this? What is the slope here? I told you also before, the slope is B capitalized, multiply B not capitalized, multiply V. I told you before. We calculated last time during the lecture. This is this, excuse me, yes, negative because the minus, in accordance with the Lenz's law. Faraday laws, we don't have a minus, we have a plus, but please apply this with minus. Why this is this value here? It's exactly the same with plus, because here is easy. Is true that from here to here we have it twice Vm. It's true, no? Twice Vm. But we have also twice the time. This means it's exactly the same, but with plus, because here the slope is negative, but we minus in the length law becomes positive. But the amplitude in absolute value is the same. The reason is we have twice phi maximum, but divided twice the time. Last time probably I clarified a little bit in different form, but it's clear. Now here is exactly like it. We can see the symmetry, no? Now, current. The current is this here divided R, because we didn't consider the elements in the circuit. In this current, the current which is generated in the circuit because of the movement, you remember what I told you last time. We have the movement, we generate the current, and we generate also the force, now we calculate. But now that is clear, yes, it's clear. Please. Now the question is, I think the next question is the power. This case is easy, the power. Okay, yes, the current, but the current is trivial. No? Is exactly the voltage divided R. I divided the value by R. Power is extremely easy because you can consider voltage square divided R or current multiplied by voltage. Using later and the time is more complex. This is the concept. Which is generated by this induced voltage. Please attention to the concept. Generated by the induced voltage, and equivalently is is transformed in temperature by the resistance. One is positive. This is which is basically calculated on the resistance, and this negative, which is generated by the induced voltage. It's the same. Now we have two powers. One is generated, and our is what we lose on the resistance. You have just two components in the. Do you remember the lecture of last time? We have an induced voltage, which is there because of the movement, and we have the resistance. What I generate with this equivalent or induced voltage is basically I lose this energy or the voltage, let me say, and the resistance. Here is just the power on the resistance, because for the convention is positive. What I am consuming is positive. What I am generating is negative. It's just the electrical power which I have on the resistance. The mean value is the same, no? Because it's constant. Very often is imported the mean value. He has no changes. P over time equals the mean value because it's a constant. What is this? This here is the answer to the question. Please graph the induced force or the eddy force or the break force. In machine, we say break force. Break because it's negative. Because to move, what is the concept? To move inside with a constant velocity, for instance, but any kind of velocity, we have to overcome the force which works against the move. The nature that don't want changes. The nature is raise power. Look what happens. This we have to remember a little bit where this knowledge came from the lab. We can measure that. Lorentz and Lenz law as laws come from observation. I measure something and not a theory. I have to mathematically demonstrate. Lorentz measures something, and then they say we formulate a law. I don't know if you remember the, let me say, the equation or the law. If you remember the law, this was basically the current. Un secondo. This means this current here, which multiply the flux density, which multiply the length, which is involved in the fields, which multiply the number of the length means n multiply b in our case. You remember when I introduced this Lorentz law, I used the letter L, the length of the conductors involved in the flux. Here, the length is n multiply b not capitalized, which multiply b capitalized, the flux density, which multiply the current. This means here's the current, which multiply n, which multiply b not capitalized, we multiply b capitalized, we will obtain this value here. Constant negative. Do you remember in the first lecture, I try to explain, you remember, if I want, I can reopen the lecture. Why this current, the force is always negative? Do you remember this? Because how possible to, I need to open because it's easy to, I try to explain intuitively and then I open again the lecture. It seems to be that here the current, it changed at the point T1, no? The direction, right? And the question is, why don't change the brake force? It seems to be at this point, if change the current, I told you that we have n capitalized multiply b not capitalized is L, the length of the conductors involved in the flux. Multiply b capitalized, multiply the current. Now, if the current change, why the brake force does not change? Does not change because change the part of the coil which is active in the flux. If you don't want to remember this, keep in mind that we have, with respect to the eddy current, always in a brake force. I mean, in this part here of the phenomenon, let me say in this form here, is valid, is true, let me say, that the current with respect to here change sign. But in this part here is involved the current of the rear part of the coil. I try to show you here what could be, let me say, better if I show you the, let me see if I am able to. Look, from here to here, we have a negative force. Why? Please pay attention. From here to here is a negative force. when all conductors says, yo, why the negative force remains negative? Because when I go out, I have seen that change the direction of the current from the graph, but change also the direction of B. Two changes maintain the same direction. You remember this? For instance, can be explained in this form here. In order, let me say, in the situation when we are totally inside, basically here, at time t3, we are totally inside, happens what I told you before. And totally inside, and go ahead, change the current, but remain negative, because now the force is given by the rear part of the conductors, in which change the current, but change also the direction of the flux. Therefore, we maintain the negative force. If I ask in the exam, we will come back on this. If I ask in the exam about the magnetic power, mechanical power, we know that the electrical power plus mechanical power equals 0. This means is exactly the electrical power with a minus. The mechanical power is the F, which I have, the unit F, which I multiply the velocity, which can be calculated analytically. Is this enough to multiply this by V? This means we have this with V squared, or directly from here. You can see, no? Is exactly the same. You can multiply this by V, or you can multiply, or you can consider this with minus, with the minus, because we know we have two forms of energy, two forms of power, electrical and mechanical. We don't have this because we are moving and we are generating both. This is difficult, though. I try to recall concept of physics. I'm not good in physics, but anyway, electrical machine. Okay. For the Mensa, our time, I don't remember. When we have to stop for the Mensa, last time we stopped 11, no, 12. When you say me? 12. It's the same, for me it's the same. No? I remember the last time we stopped and a quarter before 12. Quarter before, then we eat and then we come back. Yeah? But for me it's okay. See me. Think about another exercise. I don't know if last time I didn't propose this, no? I didn't propose. I explain the problem, then I leave in 5 minutes, and then I come back, try to do actually the flux. Because we have seen that the flux, this is difficult now. We understand it. Now we repeat everything, okay? We will, it's not so much difficult. But very often between, also last time, if you look at the lecture in the practical application, between two magnetic poles, which is inverted in auf Deutsch is umgepolt. We have a small or less small, yes, relatively large, if you think, element without that space without magnetic flux in the arterial for the reason which I will clarify. Basically, it's as before, but between the two magnetic fields, it's exactly as before, but between the two magnetic fields, we have a region without magnetic field. I tell you why sometimes we design auf Deutsch und das System zu beruhigen. But change a lot. Change a lot in the design, change a lot in the magnetic fields, in the flux, in the induced voltage, in everything. Look, more or less it's as before. It's as before because don't care about the value. Don't care about it. I don't need the value. I need the value just to show you what I give you in the exam. Same question. Flat. It's exactly as before. No? Flats involved in the phenomena. Induced voltage, induced current, power, the power, the current of the power, break force, and at the end I calculate the mechanical power, right? The mechanical power, which is equal minus the electrical power because of the Deutsch wäre Erhaltungsgrenzwert. Ne? Just wait. Take 5 minutes. I come back and we will discuss the solution together. Here, in order to facilitate, here we have what something happens. I don't show you, even though it's a shame. It seems to possible to see the solution a little bit. But at least you can see the points, the time when something happens. It's quite similar as before, but I give you another indication. The flux, once I achieve the maximum, which is exactly the same as before. If you look, the maximum is exactly the same as before, but after achieving the maximum, we don't decrease immediately the flux. We remain constant. This example, we have seen also last time in the PowerPoint, in the presentation. It's not PowerPoint, it's a LaTeX presentation. Remember, there is two cases in which the flux does not reduces immediately, but remain constant. Was a little bit different, the system. And then we decrease. Try to do, in the meantime, I try to call. 5 minutes, I come back. Try at least to the flux, because when you have the flux, immediately you have the you just want it. Minus n multiply the derivative is because if the velocity is constant, this is all. Current voltage plus the R, and then think about the power. The power is big, but it's not so before, and then the mean value of the power. Now, the mean value of the power is not the same of the power. This is the trick why I'm looking very often. We are looking for a equator in this form because we want to reduce the mean value of the power. Try to think about, and then the last question is practically equator, but try and mention this break force, and the mechanical power is minus the electrical power. Because mechanical power plus electrical power equals 0. Thank you. That's kind of we're going to be. Ready? Oh, I'll give you a couple of minutes. No? I'll give you a couple of minutes. But I've seen already good things. Think about. It could be that I have time to call again. And then in any case, before lunch, we could do this. After lunch, I plan to do another exercise, and then we will go ahead with a bit with a more realistic English. This will be the course, and then we down. Then again, comes, and then up. Nice. 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 Let's go. 2-3 minutes max.
Und sagt, Leben 1 ist Raum. Ja, Raum, das ist auch was nicht. Leben 1, sagt man 5 Zahlen, wir Frauen. Also eins wäre 1, was man muss, und das wäre 2, A, war Frau ist, warum ist 4, 3 und 5, 5 Frauen, 4 Frauen. Ja, es ist eigentlich mal Anfang. Die Frage ist dann quasi ja, genau, bei 3 und bei 2 aber die
Okay, this is the time. This is the time to do together the solution. Yeah? Did you have it? It's an interesting structure because I am going up as last time with the same time, with the same maximum flux. Because if I consider this part here, we don't have changes. Did you agree? If you consider just this means the time T1, the maximum Pm is the same. Clear? Huh? Then we have a constant part. Why that? Because the magnetic surface, active magnetic surface, does not change until these conductors are here. Did you agree? The calculation is always the same. Not the stroke, which I have to cover, divided the velocity. I think here I can comment, but stroke, the considered stroke, divided the velocity. Yeah, in particular, yeah, it's easy, no? T1 and T2, we can see that T2 is twice T1, huh? Because these elements are the same. Please pay attention now. When this conductor is here, somehow the coil is totally inside the structure. The structure, I consider this element in between, and this element, even though it seems to be that here we don't have elements, we don't have active permanent magnet, but is in the structure, belong to the particular motor or permanent part of the motor, even though we don't have flux here. This is the point T2, as I told you. Now, when the coil is totally inside, please now pay attention what happened. This is the most difficult things. I don't know if everybody did correctly. I didn't check exactly. I saw just the form, but I'm not sure if everybody may correct. What happens in your opinion? Going ahead, let me see. Why? I mean, in your opinion, this slope is the same like this in absolute values. Of course, this is negative, this is positive. But in your opinion, at the same slope in absolute value is different? Yeah, answer me. It's different. Why is different? How much is the difference? First of all, why is different? It's correct. The answer is correct. It's not exactly, I mean, we have an asymmetry with respect to this point. But yeah, I have to say that, yeah, you have to add something, yeah. Yeah, tell me.
Because we have two changes at the same time. We have the change in the negative, but also the change like
Perfect.
away from the positive.
Perfect. Basically, let me say, on the right part, let me go to the right part, we included negative flux in the coil. And the left part, let me consider so right and left. In the right part, we will include the negative, moving. We include the negative flux. And the left part, we excluded positive flux. This means we have a double contribution. Let me say in negative sense, in left, right. Now I am moving from left to right, yeah? Try to imagine. On the front of the movement, we include negative flux in this coil. On the rear part of the movement, we exclude positive flux. This means you have a double contribution in negative sense. We are going down with the slope twice with respect to the slope with which we are going up. Just conceptually. If you forget this, if you are not able to see that, we have nevertheless a way to do correctly the exam or the exercise. Think about when happens that the flux is zero. Answering this question, we can forget also rear part, front part, excluding, including, which nevertheless clarify better. If I ask you, when the flux is zero, this is easy to answer. When the coil is, let me say, in the middle position, in which we have the magnetic flux, active magnetic flux on the left, let me say left positive, equals the magnetic flux on the right negative. This means that the magnetic flux in the whole coil, we have to consider, is zero. When this happens, did you agree that this was the T2 situation when the coil is with all conductor here? Excuse me, I made this. No, it's correct. Then moving ahead, I have to cover A divided 4 stroke. When a part of the coil is positive equals the part of the coil is negative in this central position. And with respect to this one, I have to cover just A divided 4. This means the point T3 is the point T2, time point, plus A divided 4 divided V. Why phi divided 4 A divided V? Because the point T3, when the coil is exactly in the middle, should cover T2, because we are in T2, plus A divided 4 divided V. If you consider A divided V plus A divided 4 divided V, we have this 5 divided 4 multiply A divided V. Should I calculate for you? It's easy, no? The trick is try to imagine what happens. No? Should I calculate? No. Okay. Now, once this is clear, this could remain constant and can go up. The most difficult is just this. The most difficult is just this. The rest is exactly symmetric because the phenomenon is symmetric with respect to this point. So, roughly speaking. Then, voltage. It's easy, yeah? If you remember. N minus, in accordance to length, Faraday is plus, but we N times the derivative of flux with respect to the time. The derivative of the flux with respect to the time is B capitalized multiply B not capitalized multiply V. Exactly what I'm writing here. The unique problem, but it's not a problem, is here, but it's twice this, because as I told you, the slope is twice with a plus. Why it is 0? Because we don't have changes. Yeah. Wrong? Something wrong?
I just wanted to ask, at the bottom, it's negative n times lower p speed times upper p speed times v.
Yeah. This is a way to say, in the sense, the length is n multiplied b, not capitalized, which multiply b capitalized multiply v, as we analyzed at the beginning of the course. Or if you want, minus n, which multiply the derivative. What is the derivative? The slope. The slope, I told you many times today, last time. B capitalized multiply B not capitalized multiply V. Voltage 0 is clear, huh? Voltage 0. But we don't have changes in flux. Therefore, extremely important the flux. The rest is almost automatic. You can look on the data sheet in the form example. But better to understand because you also can save time if you have in mind a little bit better. But if you don't remember, you can always, sometimes also me, if you meet on the street, it could be that I don't remember. I have to look. But for the examination, should be nice if you remember. So you save time and you can go. Now, current, easy, is exactly the voltage divided R. Just quickly. The R was 10, but you don't need to calculate anything. Basically, this U induced voltage is exactly this divided by R. Please don't forget, as in my case, to write current, but anyways, it's clear, no? It's in the current. You do agree? Yeah, I forgot to write current, but it's in the current. I can write something. Now, going ahead, we are almost finished. But now, please attention. Please attention, because we have a couple of things that should be clarified. Now, the questions are electrical power. Could be positive, could be negative. If you consider positive, is the power which I consume, let me say, transform were in the resistance. And then the mean value, it's mean value. I consider always this positive instead of, we have two power. One positive, one negative. Negative is over the resistance. Positive of the resistance, excuse me. Negative is out from the you just generate the negative power. I consider always this because it's more important the design of the actuator. Because the problem of the actuator, designing actuator to work with the actuator is the temperature. The temperature should be maintained lower and lower. Because it's the temperature which damage the actuator. High temperature, this means high power, damage the actuator. Therefore, very often we give the possibility to relax the motor with this part between the magnetic elements with zero in order to reduce somehow the power. Look at this picture and let me think. What do you think about? Why the electrical, it's so. It's easy, no? Because we can consider U squared divided R. I mean, this is exactly U squared divided R, or if you want U multiply current. No? You can obtain this value and this value in both cases. I would like to consider U divided R. No? So it's easy. U squared, excuse me. U squared divided R. This was minus B, not capitalized, B capitalized, multiply V, the value of the induced voltage, negative at the beginning. If I square with positive, divided R. This was 2 times this value, everything squared, divided R. To draw the P over time is not a problem. It comes automatically. If you remember, U squared divided R. We don't have to think about it. More interesting is the mean value, is the most important parameter in the elements, in the why, in your opinion, I did this calculation? Think about it and we discuss. We almost finished. Now we go. It's easy because we have 5 intervals. Of course, it's not here clarify the question, but in the exam I will clarify the question in the sense, please calculate the mean value. Until now we did consider the whole time in which the phenomenon runs until T6. But until T6 we have 5 times T1. If you look at the calculating element T1, T2, we have 1, 2, 3, 4, 5 equals intervals. The interval is equal T1. Look at the calculation. 5, no? 1, 2, 3, 5, 4, 4, 5. When we have a 6 point, we have a 5 interval. 3 points, 2 interval. No? 6.5 intervals. This means I have to divide everything by 5 times T1. And what about this? This element here, without 6, in the surface of each element, we can see here active. 1, 2, 3, 4, 5, 6. They are all the same. just geometrical. This means you do this calculation. Ready? If you don't like to do that, please do as I did last time in the slide, in which I do the integral. The integral between here and here, this is 0, the integral between here and here of this constant, we will look that we will obtain the same. I don't know if it's clear. The mean value is an equivalent constant power between 0 and Tsx with the same surface of P electrical over time. You remember the concept of gymnasium, no? The mean value. The constant, but the surface under this constant is the same with respect to the function over time. Think about it. Now, break or induced force, break very often. Because it's always negative. We cannot be safe. You know, remember this is always negative. Why you have to remember this came from the lab? No? You remember the idea? The current, which multiply the length involved in the flux, which is N multiplied B not capitalized. The current multiply the length involved in the flux, which is N multiplied B not capitalized, multiply B capitalized. The current was minus N multiply B not capitalized, multiply B capitalized, multiply V divided R, and I have to multiply N multiply B capitalized. Therefore, this squared. Basically, takes the form of the current, multiply by minus, because it's in a bracket, this we know from the lab. We know that we have to work against, multiply by the length L in the original lecture, which is in our case N times B not capitalized, multiply B capitalized. Remember the Lorentz force was L multiply B capitalized, multiply E in the normal structure, in the orthogonal structure. If I ask about the mechanical power, is enough to remember this. This minus E electric. Excuse me, P electric. This means this with a minus. You don't need to draw, but this is enough. To remember this. Or if you want to multiply this by V, but it's equivalent to this with minus. No, in this case, without minus, without minus. Okay, I think we can take a rest now. We go to Mensa. We will come back with another exercise. So we work out on this, and then we will go ahead with the more real cases, an introduction, a real case, and then we will see in a moving coil example, an actuator, the microphone, which is we used also as an actuator for our intake valve on the model. Okay, I think we can, our time we come back, half hour is okay? 20 past, more or less? 20 past, no? Okay, more or less. We will see in half hour after Mensa, no? Thank you. Okay, let me restart. Now we do another exercise, and then I try to extend in a real case at the beginning conceptually, and then I will reopen. Remember the lecture of last time. At the end, I tried to present a moving coil actuator exactly with the rectangular coil or something like that. And we will see the real model with the differential equations without going depth on the differential equation. The differential equation models I will consider in my course of dynamical systems. For not only for actuator, for any kind of system. Okay, let me switch on the lateral camera, exam exercise again. Try to think 5 minutes about this possible configuration, again with the simplification velocity constant. This means, yeah, that we don't have to consider the mass of the mover and current constant. This means you don't have to consider the inductance of the coil. The data is written here. Think a little bit about that now we have a no symmetric situation. Let me show you. It seems to be a little bit complex, but it's not. I mean, we have the same rectangular or the similar rectangular coil. Then you have a plus A divided 4, basically as before. Then something empty, again A divided 4. Then A divided, excuse me, 2, A divided 2, A divided 2 negative. Basically, if you consider just this part, it's exactly what we have seen. Did you agree? You have seen something like that exactly now, no? Also, now there is something positive after the negative. Basically means foreign apart is exactly the same, but yeah, when these conductors are here, going ahead is different. When this conductor is here until here, when this conductor is here, we don't have to change anything. But starting, excuse me, from here, starting from here, changes. Think a couple minutes for phi. Phi is important for U induced current. It's important for everything, if you want. Also the rest, because the power depends on the voltage, the force, the brake force depends on the current, depends on everything. This means phi is the most important profile. Graph phi and its point, important point, when something changes. I give you a couple of minutes and then I will start to show you the solution. Question?
Is the flex positive, then no flex, and then negative and positive again, or we can?
Is positive at the beginning, empty as before, negative as exactly as before, and then please pay attention. The last part is positive. This means as long as these conductors are here, or until here, better to say, no changes, but from here changes a lot when this conductor is here. Ooh. Think about that.
Ja, da hast du ja auch stark, wo das Beste entsteht, der Welt wird immer wieder raus ist. Aber das Leben ist immer positiv. Ja, aber von Nachteil ist sicher, weil immer und alles ich sehe auch, dass die kaum wirklich positiv erreichen. Die Menschen und Zahlen wäre das sicher. Genau. Ist ja noch alles, was ich dann ist ja das 2 1. Was nur für Leute. Da wäre nichts bei Leute. Ja, vielleicht. Das dann ist es ja, das ist mit der Nutzung. Daran, wenn es ja nur ein großes Verein ist, dann sind jetzt Leute, die ja keinen sonst weiß. Ja, das kommt mit Works, das macht dann meistens irgendwie als Eigenbereich, das nicht, das ist ja 60% der Stoff, denkt man dann dort nach. Das heißt nicht sein. Das ist jetzt hier. Und dann geht er weiter und liegt ja direkt Plusposition. Und deswegen, weil hier mit Minus ist, was reserviert. Und ich würde es nicht unterscheiden, weil ich wieder was einmal geschaut und die muss jetzt wieder machen.
Ready? Okay. Yeah, let me show you solutions. Again, the questions are always the same, no? And their relevant point which changes, no? This is the clear formulation. No? Basically, again, 1, 2, 3, 4, 5, 6 graphs with their relevant points. Relevant means, again, points with changes. As before. The questions can be formulated with different words, but what I intend and to produce these graphs. Look at the first graph or the phi. It's a little bit small, but we can see. Now, in the data sheet, phi equals b multiplied s of t. S is the active magnetic surface, or the effective magnetic surface, or the effective surface. If you don't remember, you can look at the datasheet, but try to remember. So it's going directly. It's change over time. Change over time. One question, I received one question last week, not in this context, in the context of a bachelor thesis. What is S of t in case we have a rotational model? It's sometimes a function of sine cosine, sine or cosine. I don't have time to show you the rotational configuration, but it's easier. It's easier because once you have it's repetitive. Anyway, in my opinion, it's simple. Look. I don't know if you see. The dimension of the example which we did before was exactly the same. I don't remember now. Yeah. This means until, please pay attention, until T3 is exactly the same. Because T3 represents the time when these conductors are at this position. Did you agree? T3 represents exactly as we did before, when these conductors are in this position. I don't know if you agree with this. Huh? Until T3, no changes. Say me, okay or not? Because T3 represents the minimal flux, and then it happens when this conductor in this here, we have the maximal negative. This means once understood the exercise before, until T3, we don't have to think anything. The calculations, the value, is exactly the same. Of course, please pay attention at the dimension. It seems to be exactly the same. Now, as I told you before, starting from T3, we have the coil which is totally inside. I mean, it's totally the minimal negative in the sense, or the maximal negative as you want. And then I am going in this direction. This means I am including in the coil positive flux. You agree? I think you have an error here. Or? Let me see T4. No, it's correct. Why is correct? Because it seems that at T4, we have the flux 0. And the flux 0, I don't understand. Yeah, the flux is 0 when the coil is in this position. Did you agree? Basically, when let me say, the coil is in this position. This means when all these conductors are here. This means I have to cover, starting from this position, again, A divided 2. This means T3 plus A divided 2 divided V. It's wrong, huh? Why 4? Again, T3 was exactly as before, right? Yeah. Plus A divided 2 divided V. This is wrong. It's not 4. This is wrong, right? It seems to be wrong. Let me see. This is 0. Okay. No. Excuse me. Again, let me. T3 is here. Everything is negative. Then I'm going ahead. And after A divided 2 divided V, okay, is 0. Okay, this is 0. Okay, this is correct. When this is 0, this here, if this is correct, plus A divided 2 divided V. Okay, it's correct, it's correct. No, it's just an error. Let me do again. It's a shame. T3 is this correct as before, no? Yeah, because it's 3 times A divided 2. Now, T4, it's 0, is T3, it's correct, it's correct. No, it's not correct. I forgot 2 here. Right? No, it's here, excuse me, it's here. Everything is correct. I didn't see it. It was not visible. Okay, look, this is the new calculation to verify. It's exactly this one. It's okay. Did you agree? This is correct. Excuse me for my mistake because I didn't see this. Then why is positive? Because at time T4, I am the coil in this position, half involved in positive, half involved in negative. Now, let me say I am in the exit phase, in which I excluding from the rear part negative. This means will become positive until the maximum, as before, when these conductors are here. And then we have the exit phase, in which I coming to 0 because I am exactly excluding positive elements. We have to be careful. I didn't say this element here. Did you agree with this? Here it's before. Twice. We discuss a lot here. This is twice. Please pay attention. Everything is correct. Everything is correct. This is correct. Please pay attention. These 2 I didn't see. I verified here that T4 is T3 plus A divided 2 divided V, because I have to cover again A divided 2 stroke to obtain 0 from T3 when the conductors are here to here, and at this position we have 0 because we have half of effective coil negative and half positive. Questions here? I mean, you have to pay attention because sometimes if I don't see, it is better to recalculate. If you agree with this expression here, or with this graph, did you agree? This is easy. Just apply minus n negative. If you put, do you remember, you forget minus. This means you use the Faraday. It's not a big error, no? Plus and minus is always in a convention, but remain with length. This means if you apply minus n, multiply the slope, remember this concept here, the phi with respect to the time. If you remember, the slope is always b capitalized multiply b not capitalized multiply v. This is the slope, this is minus n. Then we have an 0 because this is, until here is as before. Did you agree? Until t3 is as before. We don't have to think about it. Yeah? Twice, because we have a slope twice. The slope here is b capitalized multiply b not capitalized multiply v. Here is twice. Here we have the same level. Why that? Because we have as before, no? Before. We have a doubled change, but a double time. This means longer, but with the same amplitude. Question here, no, we have seen also this case. No? From here to here, we have two times the maximum value, but also 2 times the interval. This means the level is the same. This here is always the level equals here, but with different sign. No? Here is exactly the entry phase, exactly the exit phase, which we have seen in the pilot lecture last time. Current, no problems, absolutely. You consider this graph and you divide by R. Please don't forget, as before, to write I, current. Sometimes I just add the current. It doesn't matter, as you know. But we have just one current here. No? Of course, we will see in a few minutes later that it could be we have 2 currents. One is the eddy current, is always there, the induced current, the current which is induced in the circuit because of the movement. And then if you have an input to control the motor, to control the actuator, we have another current in the same circuit. I show you what I intend. But it's clear, if I have an input, at this moment no input, just I push. This means we have a current as a reaction. But if you consider that I run inside, because of the input, we have both the current of the input and the current of the reaction. It's a little bit complicated, but I'll show you. Now power. Also easy, no? If you consider, you don't have to look at the data sheet. U square, U induced square divided R. Basically, is always positive in this context. This means in accordance with the convention is the power which I dissipate, better to say, on the resistance, because it's positive, which is equals, or better to say, minus the power which I generate with the U induced. One is positive, one is negative, no? In the circuit. You have 2 elements, you remember, electrotechnique. Now look, to calculate the mean value. Calculate the mean value. This is always the question. Please pay attention. The mean value of the power is always the question, because if you will do the bachelor thesis in my lab on the topic actuator, or also control for actuator, the mean value is an extremely important parameter or indicator. Because if you exceed the power for a short time, it's not a problem. But the mean value is always important because it's what remains the system. The basic power. Of course, if you exceed 1000 volts, everything is broken down. Of course, also the peak is important, but for reasonable peak is not important if you exceed also sometimes 10 volt. It depends on the structure of the motor, but the mean value of the power is extremely important because this remains always in the system which is working. And this could be a problem to dissipate the work. No? The problem in the actuator is, for the life of the actuator, is the temperature. Therefore, sometimes we use ventilator. Look, the mean value I calculate as before. We have 6 interval. 1, 2, 3, 4, 5, 6. 1, 2, 3 equals. Because here we have a T3, T4 in the middle, between T2 and T3. Then, as I told you before, I divide it in 8 surface. The level of the surface is n b capitalized multiply b not capitalized multiply v squared divided L. The trick, in order to use this compact form without doing the integral. If you don't like this, do the integral. No? Forget to divide it in surfaces with the same amplitude, let me say. This is the same amplitude like this, the same amplitude like this, the same amplitude like this, the same amplitude like this. If you don't like this way to do it, I remember I learned this in elementary school. No? If you don't like, do the integral. No? You remember last time in the lecture. The calculation is the same. But because of the constant of the velocity, we have this stepwise constant function. It's always possible. This means this amplitude with the square multiply the base, which must be always the same for everything. Multiply 8 is the total surface, because we have 8 elements active. 1, 2, 3, 4, 5, 6, 7, 8. Divided the interval corresponds to a level, to a constant, which at the end is this one, which is something like here, in which the surface under this constant equals this distributed surface. This is the concept of the mean value from elementary school, from gymnasium. But if you don't like this way to calculate with this surface, do the integral. No? Because in electrotechnics, we learn with the integral, probably. No? The mean value of the power is 1 divided T, the interval of time which we want to consider as. I didn't specify exactly the interval, but it's the interval is when I am out, no, when everything is finished, let me say. No, it's intuitive. Yeah. Integral of the power. And then you divide it. This is this one between 0 and T1 here in this interval in 0. If you do the calculation as we did last time in the slide, you will obtain exactly this. This is important because this is the level of stress, thermal stress from the power. To consider the temperature, I don't have time to tell you about that. So in some data sheet of the motors, of the actuator, we have exactly this table. No? From this middle value of power, we have this temperature. And then in accordance with our stress, we have to consider to dissipate this thermal energy, no? which is reflected by the temperature. We don't have time to do this, but I would like to give you this information because the mean value of the power is extremely important for the functionality, for control, for design, for everything. Because the critical point is the temperature. Because of course you can generate a very strong force, we can generate high velocity, but what is the price? It's the temperature. And this limits, the temperature limits the life. Let me conclude. Force or induced force, or break force. Always negative. It's impossible to make mistakes. Keep in mind. Why you have to keep in mind? Because we learned from the lab. The system don't want. At least in this configuration, because I try to push. No? If you remember, is the current multiply L, the length of the cable involved, which is N multiply B not capitalized, multiply the flux density with minus. And then, of course, if you want to calculate the mechanical power, this is minus the electrical power from this, no? For instance. Or you can consider the force divide V. No? The break force divided V. Look at this interpretation. Look at this interpretation in order to justify a little bit what we have seen also before. This is a possible further interpretation what we have seen also before. We have twice the slope. If you have 4 times the current, the force. Also the current, no, the current twice, excuse me, as the voltage, excuse me. Why that? Because in this configuration, both, let me say, both B side, B not capitalized, you understand what I intend? Contribute to the force. Do you remember I told you twice the slope? Here, we discussed a lot. Twice the slope means twice induced force with respect to before. This means twice current. Excuse me for the mistake. Twice current. Before I thought I something different. Twice current because the current reflects the voltage. But why in this configuration we have 4 times the force, 4 times the power, and so on? We can interpret it for the force in this because the contribution is left and right, or right and left. It depends. Look, it's a shame at home you cannot see. The flux is going through the table. The current here on this real part is down. The force is in this direction. If you do here, it's a shame at home you cannot see. We have something like that. Again, this direction. But the current is twice. This means the force is 4. No? I don't know if it's not an interpretation possible to. We have already seen this element. Left and right is important. In this case, both sides contribute because of the configuration of the model. Now we can understand very well why invert. Because if I don't invert, I don't move. Because if I don't invert, I mean, they have 2 forces. if I have plus and plus, yeah, I don't have this force, no? They compensate. Okay. Let me now, before introducing the differential equation, let me discuss this example in order to introduce L not zero. Remember, before I told you the example which we are doing now is for L equals 0, or equivalently for current equals 0. But current equals 0 is quite abstract, you know, because we don't have current equals 0 in our example. But we can consider L equals 0 in the sense is very small, is negligible, but basically in the motor is never negligible because the inductance plays an important role in the magnetic flux, plays an important role in the current. In any case, I don't want to go in depth, but it's easy to, probably Andreas told you a little bit about it. The inductance is always non-negligible. Now, in the example until now was important in order to refresh, in order to understand a little bit what happens in an easy form. Let me say, I can say, so when the current is constant in the sense steady state, I mean, we have seen that the current is a stepwise constant, but changes. Now, very shortly, what I would like to show you here, if L is not zero, just the concept here, and then we will do the differential equation. If the current, excuse me, if the inductance is not zero, I'm going inside the flux, I have an induced voltage, which is negative, do you remember? Because the flux is positive, but because of the inductance, the voltage and also the current, let me consider the current, does not change abruptly. The current now is not a stepwise constant anymore, but an exponential function. Do you remember in electrotechnique? The current is exponential function in an RL circuit. Do you remember this? Negative because here we have an induced voltage negative. Now, please pay attention here in order to clarify what happens in this configuration. Let assume that at time T1, the coil is totally inside. Yeah. At time T1, the coil is totally inside. At T1 plus, this means shortly after T1, that means let me show you a little bit better. I go inside, assuming that until T1, the current is going down. This means in accordance with the rule which I have. If you look at the hand, at home you cannot see very well. But until T1, we have an efforts back, right? Exactly as is indicated here. This situation. Flux plus here is going down. Plus means that I am passing through from out to inside. Current assuming that is down, we have this, assuming that, I mean, I measure a negative force. No? This means I have to assume the current is going down until T1. Now, what happens at T1 plus after T1? That I am in this configuration. I don't know if you see this dashed. But because we can see here, because of the inductance, I am not able to reach immediately the stepwise steady state constant. I mean, I don't have just R. Until now, do you remember the current I told you is the stepwise constant? Now it's not the case because we have an inertia, an electrical inertia. I need time. It's an exponential function starting from here. This means I need time to achieve 0, and I need time to achieve this steady state value, which probably I will never achieve. I mean, in this case, I will achieve because I go out. But in any case, I'm not able to spring. I don't know if you remember the concept of the inductance. This is an inertia. That's conceptually, I'm speaking conceptually without math. This means between T1 and T2, basically T1 plus after T1, we can see that the current does not change direction. You remember in the case before, the current changed directly, immediately after T1. Do you remember this? Stepwise constant function. Everywhere, that's now depend on the configuration, but also here. The current change, here for instance, change abruptly from plus to minus, from minus to plus. Here, if I have the inductance, that is not possible anymore because of the electrical inertia. We can also demonstrate mathematically, but let me go ahead in order to show conceptually what happens. This means for a while, the current does not change direction, remain on this direction. This means on this rear part, which is inside, is going up. After T2, we invert. This means it's going down. Maintain from T1 on T2, maintain the same direction for a short time. Look what happens for the force. That for a short time, we have a force that is positive. This means this break force is not totally negative, it's not totally break. For a relatively short time, we have a jerk. You understand jerk? Auf Deutsch Sturz, ne? Extremely complex, no? If you think about that. Just to understand what happens if I have the inductance, we have to consider such kind of phenomena. And of course, if I consider such kind of phenomena, this means that the force we can see from here is not constant as before, or that stepwise constant. This means we have and the force is not constant here, is not absolutely not constant here. We have a spring here. This means we have an acceleration. If you have an acceleration, the mass is not negligible anymore, the effect of the mass. Okay, that's just to flesh out an idea what happens or how complex is we have in that. The exam, I will ask now what happens now. Now I will open the presentation because I will consider now in a real case in terms of an actuator, a real actuator. We use also in the project with Volkswagen In the exam, I will ask about the representation with differential equations and something related to the differential equation, but not the solution. The solution of differential equation we will do of this differential equation, but in general, in the differential equations, we will do in dynamical systems. But in any case, I will ask about the dynamics because now, I mean, until now is important. I will put this test in the exam, but we are here to learn actuators in real application. This means, look what I am telling you now. But I try to minimize the mathematical part, or at least you don't have to solve the differential equation. We will see the differential equations not only for actuators, for any kind of systems, linear, non-linear, and dynamical systems. Here, in accordance with the time which I have, in accordance, you are third semester, huh? Of course, many of you, I think you didn't do math too, no, not yet. Could happen. Huh? Math 1, probably yes, no? You did. Math 2 also? Everybody? Okay, I can solve also a differential equation. But we will see in dynamical system, we will consider differential equation with another point of view. The point of view of system theory, control systems, and math as a mix. Let me open now the last slide. No, this example is just to introduce the concept, no? Just to what happens. No? We can see the difficulties. We can see that we don't have stepwise constant function. Stepwise, you understand what I intend, no? Stepwise. But function, which is exponential function, but did you see after T1, because of the inertia, we have a jerk. But not only this, no? Because of the exponential function of the force, we have an exponential function of the acceleration. This means when we have the acceleration, we have to consider the dynamics. It's not just a kinematic constant, in the dynamics. And dynamics means the differential equations. Okay, let me open. Did you see actuators here? The same. I hope that I copied here. Okay, if I didn't copy, I look for the semester before. Ah, no, this is the same, excuse me. Shame, I didn't copy to find the material. Here is always a challenge. Here. Okay, let me copy now. Material. So I have it. Exactly. If you remember, if you remember, let me share. Last time, we considered just a part of this four. I have to do some corrections, but small corrections. Just a part because we don't have time to do everything. But look at, we have seen many, many possible configurations. You remember we started with this real case, but this is a moving magnet. We can see it's a moving magnet. I mean, the mover consists of the permanent magnet, and the coil is in the stator. No? This is the application which we have. It's a shame, I think I don't have here. I have to look in another presentation. The idea to show you this, probably I have in the second presentation. Yeah. Let me explain this slide here, and then I will look for a more practical presentation configuration, even though this is a practical application, because this is the moving coil application, in which the mover consists of the coil, and is the voice coil system. I don't know if you know that. I don't know if you hear music. It's exactly this. This generates as an amplifier. You have it at home, this high fidelity system to hear music? Yeah, it's an actuator. This voice coil actuator. Basically, the voltage is applied to this coil, which is going inside, the winding is going inside to the blackboard, is coming back from here, go inside. It's basically this configuration is, as I told you before, is a rectangular or quadratic coil structure, which is moving left and right as before. Exactly the example which I told you before. Left and right, no? Because at least conceptually, no? Conceptually, we have a flux from here from north to south. You have a flux from north to south. It is possible to move, yes, because we inverted the direction of the flux, and contemporarily we inverted the direction of the current. This means I'm moving left and right. And I can realize the vibration of this membrane in order to generate a pressure wave, not to hear something. Of course, I have to code in terms of voltage my signal. This is the microphone. What does the microphone and transducer transform my voice, which is a wave of pressure, in voltage. This structure here amplify thanks to the membranes, thanks to the volume, everything is things which I don't know, because I never implement my knowledge in acoustic and so on. But such kind of principle, voice coil drive example or device, can be applied also for any kind of actuator. I show you an application in the model. I think I have. Now we will see that our concepts included L, because yes, it's really the thing. If you have a microphone is transducer. I don't know in German how I can say transducer. I transform my wave pressure in a voltage. Then I apply a voltage to this actuator in accordance with my. I have to dimension this volume, the length of the membranes, the elasticity. I amplify my voice. We have a voice here, and you hear something amplified. This is the principle. In fact, the microphone, they have a cable. No? I transmit voltage. I don't know the system when you have I don't know in music. No? A singer, all right. But this principle here is a moving coil, the name is voice coil. I don't know, it's not written here. Voice coil, drive, voice coil, motor, anyway. Is a moving coil actuator, which can be used for any kind of actuation. I show you now the equations. I show you now also possible application. Let me see if this is in my study. No? Let me see if I find some possible application in order to motivate you a little bit. How much time do we have? We have time, huh? When we have a last lecture? Three minutes. Let me tell you a little bit more, a few minutes. I would like to show you at least what we want to tell you. Yeah, voice coil. Look, next week we go in depth on this. Let me share. The voice coil motor drive, the voice coil actuator, as you want, which is a possible actuator. Look, this is based on the voice coil principle. The configuration a little bit different, but because it's in a cylindrical form, but I am moving the coils, and around the coils we have the permanent magnet. Exactly another form what I told you for this hi-fi system. Look, here's the motor, the block motor. You understand the block motor, no? And in the upper part we have the actuator in order to replace the cam. Cam, you understand cam, no? Cam. In the motor we have a cam. How possible in German, cam? You know cam? Is a tree bow? Nockenwelle. Nockenwelle. Nockenwelle, understand? Basically, we want to fill up the motor, the cylinder, excuse me, using an actuator, which is here. Here's the principle. Basically, this part here inside the moving coil is this. Around, we have this iron here with permanent magnet. And inside the cylinder, we have again permanent magnet here. And something ferromagnetic to close the magnetic fields circuit. The magnetic circuit, better to say. But anyway, just to understand the principle. This principle is this one. Voice coil. The same. Next week, I will tell you about the energy which we have in the system. Two kinds of energy, electromagnetic energy and kinetic energy. I will tell you a little bit about the possible representation without going in depth on this, because this is the topic of dynamical system. But in order to understand a little bit, understand the model of the system which we need now, because the system is extremely complex. We have seen how looks like the force, how looks like the current. This means once define the energy which plays a role in the system, we have to fix the state of the system. I will tell you about the state. And then here, I think LaTeX made mistakes. I see. It's a shame. Anyway, this is the picture. This is the picture. And I will try to explain this, which we have three differential equations. I am concluding, which we have as the position, X is the position of my membranes, the center of the membranes, the center here is this one, but we have an error in LaTeX. I have to look at LaTeX. Just to look at the parameter L now. It's not 0, M is not 0, R is what is as before, B is as before, N is the number of windings involved in the flux. B is the active part of the windings as before. I mean, here the number of winding is we can see here. No, we can, and B is basically through the blackboard, no? Which is involved in the flux north-south here, in the flux north-south here. B multiplied N, as I told you before, is the length of the conductor involved in the magnetic flux. And I will try to justify these three equations. It seems to be complex, but it's not. Part of them you know already. Part of them you know. The most expressions can be interpreted from electrotechnics, but we will see here the lens effect. B multiply B capitalized multiply B not capitalized multiply N multiply V, and here the Lorentz effect, which is basically is dual. Do you remember the concept of dual? We change just instead of velocity, instead of the movement, we have the force and vice versa. You remember this original concept. The rest is an RL circuit, and the rest here is in the mechanical system, which is moving. Okay, let me conclude here. Next week, we will see the model. We will see also probably some simulation in MATLAB, even though it's not required for the exam, to understand better. And then I will show you which kind of questions could happen or that could appear in the exam. Okay, let me stop here.